In lecture 5, we will discuss how to convert one flip-flop into another one. Okay, we will also discuss the general procedure, and we will discuss the different conversion. And these are the different conversion that we will discuss in this particular lecture. SR2, how we can convert an SR flip-flop into D flip-flop, JK and T, and similarly JK into other forms, T, D, and SR flip-flops, and D flip-flop into T, SR, and JK, and T flip-flop into D, SR, and JK. Okay. This we'll discuss all the cases, and if you know one conversion procedure, you can convert every other flip-flop. Okay, it's very easy to convert from one flip-flop to other. Only thing you should know the truth table and the excitation table. So this is a general procedure for the conversion, and from the given question, you need to identify the target flip-flop, or we can call it as a required one. So we need to identify the required flip-flop and which is the available one. Okay, or we can also call it as a given flip-flop. So from the problem, you need to identify the required and the available one. And after identifying the required and available, you need to write the truth table of the target or the required one. Okay, so required flip-flop. So you need to write the truth table you required. That is the target flip-flop. And you need to write the excitation table of the available flip-flop. So these two steps are very important. So don't get confused with these two steps. So you always need to write the truth table of the required flip-flop and the excitation table of the available flip-flop. So this is one of the important point that you should remember. And after that, you can design the target flip-flop by using K-map, and finally we can draw the circuit diagram. So this is a general diagram for a flip-flop conversion. So this is a available flip-flop. Okay, this is a available flip-flop. There will be Q and Q bar output. There can be some inputs, and by using this Q and the given input, okay, you can apply the Q bar also at the input side and the other input. By using all these inputs, you will get some logic function, and the output of that logic function is applied to the available flip-flop. So this is a combination circuit that we need to design. Okay, so this is the general block diagram. Now we will discuss the first case. We need to design D flip-flop from SR. So first we need to identify the required or the target flip-flop and the available one. So the required one is D flip-flop. So from the question, it is clear. We required our target flip-flop is a D flip-flop. So first we need to write the truth table of the D flip-flop. So this is a truth table of D flip-flop. Okay, truth table of D flip-flop. So we already studied all these things. So I'll simply write this D flip-flop truth table. When the D input is 0, okay, the output will be 0, or the next state will be 0 irrespective of the present state. And if the D input is 1, the Qn plus 1 output will be 1. Okay. Now we need to write the we need to identify the available one. So available one is SR, okay, or the given flip-flop is SR. So now we need to write the excitation table of the SR flip-flop. So this is the excitation table of SR flip-flop. Means for there is a transition from 0 to 0, your SR input should be 0 and X. That X are indicating the down care condition. And for 0, it's not, it's actually 1 0. Okay. For getting a 1 0 transition, your SR input should be 0 1. Okay. And in order to get a transition from 0 to 1, your SR input should be 1 0. And for 1 to 1 change, your X input should be down care and R input should be 0. Okay. So this is the excitation table of the SR flip-flop. Now we can modify the truth table of this D flip-flop by adding two more columns. So that is, we will write the SR excitation table in the truth table itself. So we will extend this truth table by writing two more columns, that is a flip-flop inputs. If it is SR flip-flop, available only is SR, means we will write the excitation table here. So now we need to identify what are the SR inputs should be given to the flip-flop to get a 0 to 0 transition. So in order to get a 0 to 0 transition from the SR flip-flop, it is 0x. Okay. And in order to get a transition 1 to 0, in order to get a transition from 1 to 0, the SR input should be 0, 1. Okay. In order to get a transition from 0 to 1, 0 to 1, your SR input should be 1, 0. And for 1, 1, you need to get a transition x 0. So now we got the truth table and excitation table, and we'll write the truth table of D flip-flop and we'll write the excitation table of SR flip-flop. Now we need to design this particular circuit. Okay, in order to design this particular circuit, we already got this conversion table by writing the truth table and by combining the truth table and excitation table, truth table of D flip-flop and excitation table of SR. Now from this particular table, we can design S and R. So first we need to write S. We need to design S in terms of D and Qn. So this is Qn and this is Qn. So from this particular column, we know that S will be 1 for the combination of 1, 0, and it will be don't care condition for 1, 1. So we are using D and Qn as the variable. So after substituting this particular key-map, we will get S is equal to D. And similarly, you can design for R, and here you can see that 0, 0, it's X, and for 0, 1, it is 1, and for all other values, it's 0. So by simplifying this K-map, you will get R is equal to D bar because it's 0, 1. So this is D bar and this is D. Here also D bar and D. So we'll get S should be equal to D and R is equal to D bar. These are the two conditions we derived by using this conversion table. Now we'll move to the logical function. So the available flip-flop is SR flip-flop. So we need to this SR flip-flop by connecting some logic function. So this is Q and Q bar. Actually, we require D, and we already identified that S should equal to D and R should be D bar. So D you can directly connect and R is a D bar. So the entire setup. Okay. So the circuit inside this dotted line will simply act as a D flip-flop. Okay. So this modified structure of this SR flip-flop will work as D flip-flop. Now we'll discuss how we can convert an SR to JK. So SR is the available one and JK is the required one. And the same procedure we are using. So first we will write the truth table of required one. So truth table of required one is JK inputs and Qn plus 1. So up to this point, so this is the truth table of the required flip-flop. Now we will write the excitation table. We'll combine the excitation table and the truth table, and the available flip-flop is SR. So we'll use the excitation table of the SR flip-flop. So now we can check that there is a transition from 0 to 0. So in order to check occur a transition from 0 to 0, the SR input should be 0 and X. Okay. And next one, 1 to 1. For the 1 to 1 transition, the SR input should be X and 0. So X 0, we'll put it in. And for 0 0, we already got it's 0x. Okay, it's 0x here. And for 1 to 0, SR input should be 0 1. So this is 0 1. And for 0 1 transition, SR input should be 1 0. Similarly, you can complete the remaining values. So now we got the conversion table by combining the truth table and the excitation table. Okay, so truth table of the required one and excitation table of the available one. So now we are getting the conversion table. Now we can design this. We can design S in terms of J, K and Qn. And similarly, you can design R by using J, K, Qn. Now, the design part, you can see that 3 variable function S you can design as a function of J, K and Qn. So it's a 3 variables. So this is a 3 variable K map, and we know that this is don't care condition. So this is 1, don't care 1. So you can see that all these values are indicated. And after indicating the values, you can write that S is equal to, so here it is J bar and this is J, and here it is Q, K and Q. So K Q bar, K bar Q, K Q, and finally K Q bar. Okay. Now we can see that first column and last column Q bar is common, so you can write J Q bar. And if you design for R by using J K Q N, so by substituting X 0, X 1, 0, 0, 0, 1. So you are getting 2 ones as a group. So this is K, and you can read it as Qn. Okay. Now we got the design circuit. So now we can implement that particular circuit. So available one is SR flip flop. So this is a SR flip flop available one, and you know that J input is your S input is J Q bar, and R input should be K Q. So by using this particular AND gate, you can implement, this is Q bar actually, this is Q. So here you'll get J Q bar and this is K Q. Okay. So this is a clock signal. Now we can design how SR to T. Okay. So the available one is SR flip flop. We need to design a T flip flop. So the truth table of T will write first. Then by looking into the excitation table of SR, so this is the excitation table of SR, we need to check the values 0 to 0 transition. In order to get a 0 to 0 transition, the SR input would be 0, 6, and 1 to 1, there's a 1 to 1 transition, it should be X0, okay, and for 0, 1, it's 1, 0, and for 1, 0, it is 0, 1. So we got the conversion table. Now we can design that. So S we can design in terms of T and Qn here. So inputs is only 1. So 2 variable K map is required. So and you can indicate the value 0 for S. This is for S. Down care 1 0. So from this you can see that this is equal to T Q bar. Okay, and here it is T Q. So S is equal to TQ bar and R is equal to TQ. Now we can draw the circuit. So here S is equal to TQ bar, and here R is equal to TQ. Okay. So we got SR to T. Now we'll discuss JK to T conversion. So already we discussed SR to all other configuration. Now we'll discuss JK to all other. So here we required flip flop is T. So we'll write the required truth table of the required T, and we need to write the excitation table of JK. So by writing the excitation table of JK, so this is the truth table of T flip flop, the blue portion. So this is 0 0. So in order to get a 0 to 0 transition in JK, the JK input should be 0 and X. And in order to get a transition from 1 to 1 transition, it should be X0. JK input should be X0. And for 0 1 transition, the JK input should be 1X. Okay. and for 1 0 it's x1. So we got the conversion table. Now we can design again. We need to design j in terms of t and qn, and similarly k in terms of t and qn. So we can directly indicate the values to variable k map. You will get j is equal to t here and k is equal to t. So both the inputs are same. So this is a very simple conversion. By simply shorting j and k, you will get the t flip flop. Okay, it's a very important thing. It's a very important design, because this concept we can extend the design of asynchronous. By using a JK flip flop, you can easily implement a T. Okay, by simply short the input side. So now we'll discuss JK to D flip flop, and in order to make the conversion table, first write the truth table of required flip flops, that is a D flip flop. We'll write the D flip flop truth table, then the excitation table of JK. So by looking into the excitation of JK, we can write 0 0 transition 0x. Okay, 1 to 0 transition as x1, and 0 1 transition is 1x, so 1x here, and 1 to 1 x0. And now we can design j in terms of d and qn. Okay, j and dn, you will get j is equal to d and k is equal to d bar. So again, it's very easy thing by simply connect the d and d bar. So here it is d and here it is d bar. So we got the logic diagram. Now we can design jk to r. So in order to get jk to sr, so we need to write the required one is required flip flop is sr. So we'll write the two table of sr, then excitation table of jk. So by looking into the excitation of jk, we can write, but there is a problem in the case of sr true table. If you write the sequence 1 1, it is invalid. Okay, so make sure that these two values 1 1 is invalid. And for 0 to 0 transition, we know that it's 0x, and 1 to 1 transition, it's x0. Similarly, you can by looking into this excitation table of jk, you can write the last two columns. Okay, now we can design this. So when you design the last two cases, you can consider as a don't care conditions. Okay, so when SR inputs are 1 1, you can put it as a don't care condition. And by using that don't care condition, first we can design j. So if we design j, it's 0 for 0 0 0. For 0 0 0, it is 0, and for 0 0 1, it is x, and 0 0 4 0 1 0, it is 0, and 0 1 1, it is sorry, don't care. So it is don't care, and after that you can say the 1 x x x, so 1x, and you can make a group of 4, and this will be equal to j is equal to s. And similarly, if you design for k and indicate the value k in this particular table, so you will get again a group which is k is equal to r. Now we got the logical diagram. It's again very simple. JK flip flop can be converted into SR by simply S and R. So from this, you got an idea that the conversion of from JK to D, T, S, R are very simple. To convert T to T, simply short the JK inputs. Okay, and for D, simply note the input and given to the JK inputs, and SR directly given. So it's very easy to design the other flip flops by using JK. Now we'll discuss D flip flop to T. So here we can see that this is the required one. Required one is T flip flop, and we'll write the two table of T first, then the excitation table of D, because the available one is D. So this is a excitation table of D flip flop. So here you can say the 0 to 0 transition, D input should be 0. 1 to 1 transition, D input should be 1. And from 0 to 1 transition, 0 to 1 transition, D input is 1. Okay, and 1 to 0 transition, it's 0. So now we got the last column. Now we can design D in terms of T and Qn. So two variable, so we'll get two ones here, and one is T and Qn bar, and other one is T bar and Qn. So if you write these two things, T Qn bar plus T bar Qn, it's simply an XOR operation. So T XOR Qn. Okay. So here you can see that T and Qn. So here we get T XOR Qn. Okay. Now D to SR. So to implement SR by using D. So first write the conversion table by writing the truth table of SR flip-flop, because it's a required one, and available you need to write the excitation table. So available one is D flip-flops. So by looking into the D flip-flop excitation table, you can fill. So when there is two values 1 1, so it's invalid. Actually there is no state change we can predict, so we'll consider these two values as don't care condition. So substituting all these values, you will get two groups. So this is one group, and just simply S, and the other group we can indicate as R bar Qn. So if you combine the min terms, you'll get like this. So this is R bar actually, and this is Q. Sorry, this is Q. So you'll get R bar Q, and this is R bar Q. So we'll get S plus R bar Q. Okay. So this is a conversion logic. Now we need to implement, it's not logic diagram. Okay. We need to implement JK by using D. Okay. So first we need to write the required one. Required one is JK. So you need to write the two table of JK, and the available one is D. So we'll write the excitation table of D. Okay. And by looking the transitions, present state and next state, we will write the D inputs for corresponding values, and we'll write the K map and we'll simplify. So here we'll get two groups. So this is one group which is indicated as so after that you need to design D in terms of J, K and Qn. So this is K bar Q, this is Qn. Okay, this is also Qn. This is K bar Qn, and if you write this, it becomes J Q bar, Qn bar. So you can combine these two. So it will be like this. This is K bar, and this is Q. So you'll get K bar Q here, and here it is J, and here it is Q bar. So J Q bar. If you perform the OR operation, J Q bar plus K bar Q. Okay, this is the D. Now we'll discuss T flip-flop into different configurations. D to T, sorry, T to D. So we required actually D flip-flops. So required flip-flop is D. So write the truth table of D flip-flop first, then the excitation table of T. So this is the excitation table of T. So you can change the verify the transition 0 to 0 occur when the T input is 0. So T input is 0. 1 to 0 when the T input is 1. Then 0 to 1, 0 to 1 again 1, and 1 to 1 it's 0. So 1 to 1 it's 0. So we got the last column, that's excitation table. Now we can simplify the T by using D and Qn. So D and Qn. So finally you are getting two ones. So it becomes D Qn bar plus D bar Qn, which is again XOR operation D XOR Qn. Okay. So either you can write in this way, this is D XOR Qn, and or directly you can write. Okay. So this is D bar and this is Q. So this is Q. So you can write D bar Q, and here it is D and Q bar. Okay. Now how we can write the T to SR? So for that, write the truth table of required one. Truth table of the required one is SR truth table, and write the excitation table of T. So by looking into this, you can design T in terms of S, R, and Qn. So from this K map, we can see there are two groups. So this is equal to RQn, and this is equal to S and Qn bar. Okay. Now we can design that. So this is R, and this is Q. So RQ, and here it is SQ bar. So you can say that SQ bar. So at the output side, we'll get SQ bar plus RQ. So now T to JK. So for that, you need to write the required, that is JK. Write the truth table of JK first, then write the excitation table of T by looking into this particular table. So 0 to 0 transition, 1 to 1 transition, by looking into this excitation table, you can fill the last column. Okay, now we can design that also. Again, two groups you are getting. So T becomes, so this is J, Q, N bar, and this one is equal to K, Q, N. Okay. So you are getting two types. So this is a equation, this is K and this is Q. So KQ, and this is J and Q bar. So JQ bar. So after combining these two, KQ plus JQ bar. Okay. So that's all.